I think we got some requests that classes are going beyond time, at least on Wednesday and Friday, right? Wednesday we are taking even 11 to 12 slot, and Friday we are going beyond one. So from this week we will try to restrict. We were trying to complete the important points before the break. Now we will try not to use too much time. Okay, so today I will not take more than 11, 10, I hope. And Friday class, see what happens is a tutorial, lab tutorial. So sometimes you may have questions, it may go beyond. So if you want, you can discuss with the TA that if that class can be shifted to some other time, like 5 to 6, if all of you are available. That is fine for us. Okay. So something like that we can do. So on that Friday, when we have tutorial this time, I'll ask you if you want it to be shifted to 5 to 6, we can do that. If you think this is fine to continue up to 1:30, 1:15, we will do that. Okay, yeah. That was all the logistics. Now let's do the theory. So today we are doing heaps. So from the name, you can see it's a data structure. Right? Another very important name for that is priority queue. It's an abstract data type. Okay. And this you will find it has a lot of usage in greedy algorithms. So generally you will see greedy algorithms, you use priority queue a lot, and that helps in getting more efficiency. Like the greedy assignment 7, right? The first problem. What was the complexity you got for first problem? I think it was order n square.
Order n square, sir.
But if you can use heaps of priority queues, you can get order n log n. You can get a better efficiency for algorithms. Okay. So anyway, this tutorial, again, we will discuss a greedy algorithm where heaps can help you to get better efficiency. But let's see what are heaps, right? Good thing about it is that it is very easy in implementation. You don't have to learn new pointer-based things, and we will see why. Okay. So yeah, it's very easy in implementation, but very good in efficiency. Many, many problems. So what are heaps? So heaps. Now heaps are just binary trees with a special property. Okay. Remember I said binary trees with the special properties are very interesting. Heaps are again binary trees with some special property. And what is that? So a heap is a binary tree with the following properties. So you see, when we talk about binary tree, we have a particular structure for that, right? If you remember, I talked about a few structures: almost complete, complete, full, right? So now we will use some of this here. So the property, when I say property, there is something about a structure. What is the structure of this binary tree? And there is something about the values, the way you store values there. What is the property the values should follow? So what is the condition with the structure? So the heap is, so it is an almost complete binary tree. Anybody remembers what is the almost complete binary tree?
Except the leaf nodes, others have two shades.
No, that was full
Except the
binary.
last level, every shade has two, and the last level can have
So
one
what
or
happens in almost complete binary tree? You start filling the nodes from top label to down. So each label should be completely full. Only in the last label you may have some nodes empty, and that also you have to fill from left to right. So I'll again write that. So thus all but the last label must be completely full. Okay, and in the last label the nodes appear to the left of all empty positions. So you fill it from top to bottom, left to right, that's all. So top to bottom, and each label left to right. That's how you can remember this. Top to bottom, left to right. Okay. What happens with the values? This is about the structure. What happens with the values? So what is the restriction of the values? So for any node U and its parent P, what happens? Now, so again, so heaps can be of different types. So we generally talk about two heaps, max and min heap. So I'm giving definition for max heap. So accordingly, we can see for min heap. So for a node U and parent P, what happens? The value of parent will be greater than equal to value of the node. Okay, so that is for max heap. So that means for any node, the value is larger or equal than any node in its subtree. That's all. That's all. If a binary tree satisfies these two properties, the structure almost complete, top to bottom, left to right. Values for any node, its value should be smaller than its parent, or the parent value should be larger than the children. If it is satisfied for all the nodes, that's a heap. Okay. So now let's see an example. So accordingly, you can write min heap. So in min heap, what will happen? Value of parent will be smaller than value of child. Now let me take an example, very simple example. So is that a heap? You will see first structure property. Is it following structure property? This is label
Yes,
0.
Yes, sir.
Label 1, label 2, label 0 and 1 are completely full. In 2, nodes are filled from left to right. Okay, the structure is followed. Now value property, for each node, the value of the parent should be higher than the value of the children. So yes, 100 is larger than these two children. This is larger than these two children. That's all. So okay, so that is a max heap, and it's a max heap because it's larger. So this is a max heap. Okay. So then we can write some quick trivia about the heap. So that is, I can say a max heap of label L, that is max label. Sorry. Max label L contains, so if the heap has a max label of L, so you can easily say how many nodes it contains on label 0, 1 to L minus 1. So it would contain 2 to the power 0, 2 to the power 1, 2 to the power 2, the maximum possible nodes, 2 to the power L minus 1 nodes at labels 0, 1, 2 up to L minus 1. Right, we can say that each label will contain the maximum capacity, but the final label and label L will contain how many nodes? What is the range?
So 1 to 2 to the power.
1 to 2 to the power L nodes. Any of this number. Simple.
Sir, so instead of 3, we could have 30 also, right?
Instead of?
In that tree, instead of 3, we could have 30 also.
Yes, you can put 30. And you can check. This is in max heap.
Okay.
I can put 90 here. Right, means, yeah, you can try a lot of things. So as long as it satisfies the properties, it's a max heap. Okay, now next question. How to represent the max heap? Binary tree, we used a special structure, tree structure, where I need pointer to the left and right, right? But for heaps, do I need to use pointers? Do I need to use binary tree sort of a structure? Can I do something simpler? What is important, like in binary tree, from a node, I should be able to access children, parents very easily. In binary tree, we used to have pointers for doing this. I have pointed to the left and right child. In a max heap, what will I use the same thing as I was using in binary tree, or can I do something different?
So we can start numbering the nodes left to right, top to bottom from 0.
Right. So here is something interesting. So let me number them. Very good. Let me number them. So let's number them left to right. I mean top to bottom, left to right. Let's say 1, 2, 3, 4, 5. Very good. Okay. Now, do you see something interesting? If you know the number of a node, can you tell where will be the left child of that node? So suppose you know.
So for
Mhm.
x, it will be at 2x and 2x plus 1.
Very good. So if I know the number, like say 2, the number of that node is 2 in that ordering, then its left child will be at, so suppose this is number is x for a node. So its left child will be at 2 times x, and right child will be at 2x plus 1. And you can verify here. 1, left child is 2, right is 2 plus 1, 3. Left is 2 times 2, 4. Right is 2 times 2 plus 1, 5. And you can see, even if you had children here, 3 times 2, 6. 3 times 2 plus 1, 7.
So like why it is happening means I
Why?
cannot visualize it. Why
I'm
is
sorry?
this happening, sir?
Oh, we will discuss it, why this is happening. But yeah, you can see that, right? This is happening. Why that is happening, we will see. And what about the parent? If you node is numbering x, what is the parent numbering?
Floor of x
X by 2.
Just x by 2. I mean, if you just do x by 2 in your programming, you will get an integer. But in terms of preciseness, you can say, okay, floor of that.
Sure.
In your code, you can just write x by 2. That will give you the parent. But here, the floor of that. So verify that. For 5, 5 by 2, floor 2. 2 by 2, floor 1. 3 by 2, floor 1. Right. Good. Now question, why is that happening? Right. Why is that happening? That happens because of the property that they are completely full, and each node contains double the nodes of the previous level. That's all. That's all is the reason. This node contains one node, this contains 2, then it will contain 4, 8. So it's double the number. So when you go to its children, it's just double the number and double the number plus 1. That's all. Does that make sense? You can also prove it if you want, but yeah, that's a very simple reason you can see. Because you are filling them completely, each label. That's why you just do double and half, you get the children and parents, right? And that gives some relief. Oh, I don't have to use pointers here. I can just use a simple array. Okay, I can just use a simple array. Okay. How to represent a max heap? So, and see, this is happening because of the structure property. Value property is not very important here. You should see. It's only because of the structure property that I can represent that as a array. So because of the structure property, I can just use an array to represent a heap. Okay, so so how exactly? So what is the so we do a numbering. So numbering would be, okay, first you put all nodes at label 0, then all nodes at label 1. This will come from left to right, label 2, left to right, and so on. That is the numbering you have to follow. Okay, and you can start it from 0 indexing. We will do 1 indexing, but it does not matter. 1 indexing just to correspond to what we have shown. But so we will use a 1 based indexing here. So that means, so the 0th element will be empty. It will not contain anything. It will not be useful. So we'll start from element 1. So for that heap that we showed, so 100, 50, 90, 100, 50, 90, then 10 and 30. 10 and 30. So this is 0, 1, 2, 3, 4, 5. 5 elements here. Top to bottom, left to right. And then you can quickly see that, yeah. So we will just, if I have element, so for a node at index I in the array, we can find its left child at index 2i, right child at index 2i plus 1, and parent at index I by 2, floor or without using this bracket if you are writing in your code. Fine. As simple as that. That is the representation of a heap. Okay. Now, next question. Fine. So we have a heap, nice thing, but what can we do with that? So for that, remember, I talked about a concept called ADT, abstract data type. What is an ADT? In an ADT, you generally agree on a set of operations that you need to do. So here I'm talking about something called a priority queue, ADT. It's another name for heaps. Okay, people also call that heaps. So priority queue, ADT. So what is priority queue? What does the name tells you? Priority queue. The name itself tells a lot here. Heaps may be something, yeah, you do not know what that would mean, but priority queue you can easily relate. What would that mean? What kind of scenario that comes to your mind when you see something like priority queue?
A queue in which
We
the
can
items are sorted according to the priority
Mm-hmm.
or the importance.
Mm-hmm. Okay, and
So sir, it take the elements using their priorities, sir.
So
when
the priority. So that means what would happen is in a scenario, what will happen? So think about, so we used to talk about activities or jobs in greedy, right? So think about a lot of jobs. Okay, so some tasks like your coding. So you have a lot of different codes that you want to run on a server, like that. So think about a lot of jobs, okay? And each job has a priority number. It's just a number. That means if it is high, that means that's of a higher priority. If it is low, that is of lower priority. You yourself may have 10 different codes you want to run on the server, but then you want to tell the server, no, this code is of more priority than another code, right? So you assign various priority numbers with different jobs. Each job is a priority number, okay? And the server has to have some schedule. We are not talking about that, but it has to take care of this priority. So it should know which job has the highest priority at every time. And jobs can keep on coming. So jobs can keep on coming. So that means at any point of time, it should know what is the job with the most priority at this point of time, right? It needs to schedule that. And whenever a new job comes, it has to put that in appropriate position, right? So we have three important things. So let me write again. So one is find the job with the maximum priority. Find the job with the maximum priority. In all the jobs that you have, okay? So I will call that find max. Second, you want to take the job and schedule that. So you will only schedule the job with the maximum priority. So that means remove the job with the maximum priority. And this I'll call it delete max. And third, new jobs can keep on coming. Okay, so whenever new job comes, put that in appropriate position. So insert the new job in appropriate position. And this we call it simply insert. So if you simply have these three things, you have a lot of jobs, you can find the max of these, you can delete the max, and whenever a new job comes, you can put that in appropriate position. You have all the operations you need for priority queue. So this is all the operations you need for your priority queue. Now the question is, fine, they look very simple operations. What are the things I can use? Okay. I have to put in some structure. I have not told the structure here. Okay. It will be heaps finally, but yeah. So I have not told the structure here. So suppose you have this ADT where you are told these are the operations I need to support. And you have to think about what kind of data structure I should use. So you can think, oh, let's try simple things. So let's try simple things. So I have three operations: find max, delete max, insert. Simplest thing, what you can think? Unsorted array, just an unsorted array. Unsorted array. How much time find max will take in unsorted array?
N.
O of n? Yes, find max, find min, O of n. Good. Delete max? You found the max, and now you have to delete it.
That O of N.
Yeah, O of n, or
So
suppose
O of
you can
n.
also afford to keep that place empty. So this will be O of 1. Insert?
Insert sir O of n. O of 1.
O of 1.
O of, yes sir.
1. Because you can always insert the last index at the end.
Sir,
Yes.
So if we delete the max in O of 1, then shouldn't we, we are losing the property of heap, right? This. Because if we remove it and don't move the remaining array to front, then the property of this tree is
No,
lost.
in unsorted array, there is no problem. See, I'm talking about unsorted array. I'm not talked about heaps till now. Unsorted array, if you delete an element, put a flag, what is the issue? In an unsorted array, I'm saying.
But sir, for finding the index corresponding to the maximum element, we need to do ON work.
Yes, so that is your ON.
So,
Find max is ON.
but for if we conduct delete max operation, first we need to find the index of the element where max
No, I
is
agree with
present.
you. But you see, remember, like we were doing disjoint sets. So that's like you have to, generally the way it is done is you first find max and then you go to delete. So you have done find max before you do delete max. So you already know the index of max, you have to just delete it now.
So means we just maintain whether that means flag whether that element is present in array or not, right?
Yeah. Then you delete means
Sir.
you simply replace that place with a flag, say minus whatever, a new flag, saying that yeah, this element is no more there.
Okay, sir.
Just a flag. That should not be one of the values that you're using. Okay, if you're using negative integers, it should be something else. So just a flag. Okay, sorted array. In a sorted array, how much time find max takes?
Log n.
Find max in a sorted array.
1.
O of 1.
O of 1.
Sorted array, right?
O of 1.
Delete is also O of 1.
Yes, sir.
Sir,
You can
I
also
have
store
a
what are
doubt
the
here.
indices up to which you have deleted, so that find max remains O of 1. Okay. Insert.
Insert, sir. Big of n, sir.
Insert is going to be better than ON.
ON.
If you have to maintain the sorted array property, insert will do O of n. So yeah, both of them were fine. Just one of the operations are ON. Okay.
Sir.
Now when yes.
Sir, while deleting the object, we won't change the index of the remaining elements, sir.
Yeah.
So, sir, means it would take big of n time, no, sir?
No, we are not changing. See, I'm saying what is the best you can do. Of course, if you want to remove that and change all the indices, these will take O of n time. These both
Yes,
will
sir.
take O of n time. If you want to remove them and adjust all the indices, we are saying
Yes,
okay,
sir.
you can make an assumption that okay, wherever you're deleting that element, so this is the element, you just put a flag. So this does not exist anymore. That deletes it. Okay. That's all. In sorted array, you can even say, okay, you can store this index up to which the elements are deleted, so that you can do find max again in O of 1 time. That's all. Of course, if you have to delete and rearrange, it will take O of n time. But I'm just saying, yeah, if you can manage with a flag, it will take O of 1 time. Still, we are not good because one of the operations is taking O of n time. Here, find max is taking O of n time. Here, insert is taking O of n time. Now, what we are talking about is heaps. In heaps, we will see find max will take you O of 1 time, delete max will take order of log n time, and insert will take order log n time. Okay, and that's where our binary tree will come into play. And log n you can immediately connect with the height, right? Let connect with the height. So this is simply nothing but order height, and height is log n. In a almost complete binary tree, height is order log n. Height is order log n. Because all labels are full except the last label. So you can easily see that height is order log n.
Excuse me, sir. Excuse me,
So
sir.
what we will do in this case by using heaps, we will do find max in order 1, delete max, insert both in order log n. That's what we will do. Yes.
So we are always assuming that delete max will be implied after the find max.
Yes. So generally that's what you do. So you delete it only when you find it. Okay. So but in you see
Sir?
heap, yeah.
Sir, I mean find max, how can you say it's order 1? Because in heap you said that the value should be less than, but you didn't say it is sorted.
Right. That's all is needed. It's not sorted. The value of a parent is larger than the value of its children. That's all.
What is this? A find max, I said.
See, in Feynman, you can accordingly think, right? In Feynman, in Feynman, you will have admin heap. If your priority are like lower to higher, you want lower value to be having higher priority, you can do the same thing with Feynman. So, right now,
I mistook it for find instead of find max.
so here, I'll just talk about max heap. Analogously, you can talk about min heap. Analogously, we can talk about min heap.
Sir, can you go to the previous example where we filled this in an array? Yes, sir. Here, yes, sir. Here 150, 90, 10, 30 are there, right?
Yeah.
If we do this priority query here, operations here, then we will reach 150, 90 and remove them. But then we have 10, which is not greater than 30. Then are we not?
Why are you assuming that we will remove left to right like that? I said delete max is order log n. So we will do something else, right? Otherwise, delete max would have been order 1. If I just have to remove that, this will be order 1. No, this is order log n. So I will explain to that what we are doing. I have not explained these operations. Okay.
Sir, I'm asking about find max.
This is to do. This is to do for me. This is to do for me. I have to explain to you how they are order 1, order log n, order 1. Okay. Your question is very valid. If you do simply like that, it will not happen. So how will it happen? That's what we will see. Okay. Any other question? Then we will then directly come to these 3 operations in heaps.
Sir?
Yes?
Sir, in the previous example, the heap example that you have given.
Yeah.
Sir, here, suppose if we want to insert 99. Sir, in that case, sir, we need to shift all the elements.
See, you are thinking this is an array. I am using an array, but this is a binary tree. So why will I use an array to insert when I can do insert in a binary tree using the height? That's the idea. That's how you get order height. Otherwise, what was the use of saying about what's a binary tree? I could have just said it's an array. It's a binary tree. So now we have to think how we can use binary tree property. Forget array. Array is only to help you implement. Okay. Array is only in each of implementation. You can do the same thing using left pointer, right pointer, parent pointer, if you are happy with that. Okay, you can do the same thing with that. Yeah, that may create, I don't know whether that will be more inefficient, but I mean, you can do everything that you can. But you can use an array, that's a good part. But otherwise, just a binary tree with some special property. So when you do insert, you are doing deleting, don't think of doing it in an array. You have to think doing it in the binary tree. Sure, so let me just tell you how to do that. Okay, but yeah, good, you are thinking like that. So now my task is these 3 operations: find max, delete max, insert. Find max, delete max, insert, and I'll take a max heap. Find max. Do I need to do anything for find max? What is find max?
The root.
The parent.
So if A is the array, you take A1. If A is there, take A1. That's all. So it's an order 1 thing. Right? 100, 50, 25. I'm just changing something, 30, 20. I have to find max. I know that's in the root of the binary tree. And where is the root in my index? That is at A1. So that I can do that in order 1. Nothing else. Find max in order 1. Okay. But delete max and insert are slightly involved, not much. You have gone through BST, they are nothing compared to BST. Okay, what do you do? So okay, before I tell how to do that, I'll tell you the rule. What should be the rule? Okay, and once you know the rule, it's very, very easy. So what is the rule? How to do an operation where you have to change few things? So the rule is this, the rule of thumb. Important. when you're doing these operations, first ensure structure property. First ensure structure property. Ensure the structure properties holds whatever we have explained about here. Second, ensure value property. Do it in that way, and then you see this will be very, very easy. Let's say delete max now. Delete max. Now let's talk about delete max. I know the element at the root is the max value. I have to delete that. Okay. So let's say I have to do delete max on this heap. Okay, so that means I have to delete 100. Now, what other things I should do? Can someone tell? First, ensure the structure property. First, ensure the structure properties. What you should do immediately.
So take rightmost leaf of last level.
Right. So suppose you know the size of the heap. So suppose you know the size of the heap. Okay, size will be the number of elements. This will not be array size, heap size. Okay, array size will be right now one more than that. So take the element a size. So that will be 20. Yes, and put that element at the root, and put that element at the root. So what do I mean? So copy the value of the last leaf node, that is a size, to a1. So a1 will be a size. That's all. So and then size will be -1. So size minus. So two things. Okay. For now you see that now what will happen then? So let me now draw the resultant thing. It's not actually a heap, but let's see what is that. So I'll get 20 here, 50 here, 25 here, and 30 here. That's all I got. Now ensure that this follows structure property. Does it do? The way we have defined it, it will follow structure property, because what we are saying, you will take the last leaf node, remove it, and put it at the root, the value. Okay, that means, yeah, it will be top to bottom, left to right. Only the rightmost we are removing, no problem. So it follows the structure property. And that also means subsequently, whatever you do, don't change the structure. So subsequently, only change the values, don't change the structure. Don't change the structure. Okay, got it. Fine. So now this is the intermediate thing where structure property is followed. Now what should I do? So now see, what is it, the max heap?
No, sir.
Not a max. So now putting the last leaf at value at root will violate, I can say may violate, but let's say will violate the value property. So that means what you do now, you have to do some adjustments. So adjust the values. How? Tell me, what will you do?
Find maximum among the two childs and swap its value with it.
Yes. So what you will do? Okay, you start from the root. Okay. So what is that? A1. Now let me just write in terms of root. A of R. Now you say, okay, what is the maximum value among the two children? So now let's see, in the children of 20, 50, 25, which one is having the maximum value? This one. 50 is larger than 25.
Left here.
So what I will do, I'll swap this value with this. So I'll swap these two values. Okay. So find max value among children and swap this with the max value of course if the current value is less than max. Otherwise you should not swap. That means if you find the max of the two children is already smaller than the root, you are done. You have nothing to do. Okay. That means in else case, you are done. Else case, you are done. So what I will do, I will find out the max of this 50. I'll swap this with this. So I get then 50, 20, 25, 30. Is that a max heap?
No, sir.
No. So again, you have to
No, sir.
do this the same thing again. Compare this value with the value of its children. Now, in this case, there's only one child. So you will find out if this child has a value larger than this. If so, swap. So then you again swap and you get 50, 30, 25, 20. That's your final answer. You don't have any more child. This is a maximum. Delete max. Is that clear? Are there some doubts about this?
Yes, sir. Sir, for the 20 and 25 thing, like we will place the current pointer always to the swapped value and we will not check the other child, right, sir?
Tell that again.
Sir, when we are swapping 20 to 50, then we will place the current pointer to the 20 and we will not check the childs of 25.
See, that's the thing. You are not doing anything with pointers. You are just doing in an array. You are swapping in an array. That's all. There's no
Yes, sir.
pointer.
So, sir, while swapping, we also have to check of 25 also that whether it is great.
No, you don't have. You don't have.
So, sir, how we will ensure that we are not checking of 25?
Okay. It's a good question. It's a good question. So I'll explain that. See what is happening. So think about it. What is happening? You have a heap. You have max heap. Now you are doing delete max. So this would have a left subtree. This would have a right subtree, right? And what you do, you take the rightmost child, this one, and delete this and put this value here. In principle, you do nothing but just replace A1 by A size, and size is minus minus. So size is size minus 1. Now you have done that. So it will violate, it will most probably violate heap property. It violates heap property, value property. Then what do? We say, okay, fine. Now let me check among the two child. Now can you say, now see, one very important point is these two are max heaps. These two are already max heaps. This is a max heap, and this is a max heap. Even after the removal, can you see that they are max heaps themselves?
Yes, sir.
So now, once you find out among these two, say this child was larger, what you are doing? This is larger than this, so you are swapping these two values. So the left child comes on top, the right child remains here, and the current root comes here. And then, this subtree does not change, and this subtree only the root is changing. If this is what I call as root, left and right. Is that what is happening?
Yes, sir.
Okay, now you see. This value is larger than this value. That's why we have put it. Left was larger than right. We have swapped the root with the larger value.
Yes, sir.
Okay. So this is fine. And this is a max heap anyway.
Yes, sir.
So it follows all the properties. No problem with this. We will not do any change. Once we go here, once the root goes here, nothing will happen to this. This will remain as it is. No value change now. So this is a max heap. Done. Nothing to do. This left. This is larger than this. So this part is done. Now.
Yes, sir.
And this is the maximum value now in the subtree. That also you can see, because root, its children will be here, and their children will be smaller than them. So this is the maximum value now in the heap that has come on the root. Now the only thing that can happen in this heap, this value may be smaller than some of these values.
Yes, sir.
Yes, we can simply apply the same logic.
Sir, so yes, means that's what I was asking, that while swapping, we have to just check the values of its means the swapped value only. Like we have swapped the left and right. So now we will check of only the swapped value, like only the root. We will not check the other values.
Okay, if that was not clear, yes.
Yes, sir.
Okay, let me make it very clear. Sure. So now what you will do? So again, this root you will compare with these two. It's left and right. Find the max and swap the max with root if it is larger than the root. Same logic you will continue until you find there is no child, or you find that the larger of the left and right is smaller than the root. Then you stop. Okay. So what you do? Okay, I'll again write. So placement of the last leaf node at root may violate the property. In that case, what you do? Find max of left and right child and swap this max with the root. Okay, and then you continue doing that. So with the root only. So with the root will now go at a new position. So again, you keep on doing it with this children. Okay, so you will again find out if you want to swap with one of this. Yes, you swap it with this. Fine. Again, say it's left and right. You may swap with one of this, left and right. Swap, and then yeah, then you're at the leaf. Nothing else to be done. And whatever you are leaving, everything else is an max leaf.
Sir,
Yes.
that since we have taken the value from the very last level, sir, can we say that the swap function will continue for L times?
Yeah, means L is log n. Yes, L is log n. So swap will continue at most L times. I cannot say it will take L. It will take L minus 1 swaps. No, it will take at most L minus 1 swaps.
Sir,
Yes.
if we remove the if we means impose additional constraint that we have only distinct nodes, then it will also be exactly L minus 1 swaps.
No. No.
Why is that? Since
Good, very good.
So
very
means
good.
they are saying that it will reach the bottom of the tree. That's what they are saying.
Yeah, I understand. So they are saying it will reach the bottom of the tree. I understand that. Okay. So I'm just telling you, see, it's not always true. Why? Let me try to make a I don't know whether I can create a counter example. Let me try. Okay. If you get the idea, you can create a counter example. Okay, let me try. Maybe that is the case. Let's see. I'm not sure right now. Let's see. Let me try something like 25, 50, 10, 5, 30. And you are doing delete max. In that case, anyway, what will happen? This 30 will come here. Then max is this, so it will swap with this. 50 comes here and 30 comes here. There's nothing else here. So yeah, it will not go because it's already leaf. So it will not go beyond that. Right? So here there are L minus 2 swaps, but that is just because there was nothing here. So, but you see, it might happen. So let me put one more thing here. So suppose this was 30, another is say 40. Okay, so now what you will do, you will delete this. So what will happen? 40 comes here, 25, 50, 10, 5, 30. Now 40 you will swap with 50. 50 is the larger. Yes. So you will get 50, 25, 40, 30, 10. Will you swap any further?
No, sir.
No, right? So you see, in this case, you are doing less than N minus 1 swaps. And you see, why does that happen? Because you're not putting any constraint between the left and right. So left and right can be in any order. So it may happen that left is larger than right. You see these values, these left and right are larger than this node. So I'm not saying that all the values on a higher level will be larger than all the values in the lower level. No, that's not required. Only what is required is pairwise with the node and its child. They should follow the property, but otherwise this can be larger than this. I think when you said this will take L minus 1, you were not thinking about this case. You were thinking that all the values in L minus 1 will be larger, then L minus 1 will be even smaller and so on. Right? That may not be required. And you see the last value may be larger than just the second value. And still it's following all the properties of it.
So it shall take L or L minus 1.
No, at most L minus 1.
So,
Oh,
but
okay.
in place of 30, if there is
Fine,
45.
fine. You also took that swap, right? I agree. This swap also you took, yeah. So it will be L. Okay. At most L swaps, so this will take order order.
So if in the place of 30, we have 45. Then we have 3 swaps, including the initial swap.
They happen, they happen, like now you can play like this. So in 30 we have 45. Then what we would have done, this would be there, this would be 45. Now you will do a swap. This will be 45. You have to swap again, yeah. You have to swap again, you will have one more swap. Okay. But I gave you this where you will have less swaps.
In this case, we have L plus 1, right? Here L equal to 2. So
Yeah, I'm sorry. By L I was taking 3 sometimes, so yeah. L plus 1. L plus 1, if you take the first swap of, yeah, doesn't matter, just plus 1, but yeah. If you're taking this as a swap, 1, and then there may be L because, yeah, this is 0, 1 up to L, so that's right. So there are L plus 1 swaps at most. So this is still order log. Order log. And is the number of nodes. Is that fine?
yes, sir.
Yes, sir.
Okay, good. So I guess, yeah, today I'll leave you early. And tomorrow we will continue from here for the other 2 operations, that is insert and, yeah, insert. And we will then see one more interesting thing about heaps. Okay, any question? But your last question was very interesting. I did not think about it earlier. Okay, good.